So this is just going to be an introductory talk about spectral sequences. This is going to be very similar, at least for the first part, to introductory talk I gave on spectral sequences last year, or I forget. So if you were there, then this will be a repeat, but that's okay. The primary reference for this talk is this book by Bott and Tu on called Differential Forms in Algebraic Topology. Actually, the reason I kind of went to this book is because there's a student who I can't remember. Well,
that's Emilio. He couldn't. Make
That's
it.
Emilio.
Yes,
oh, okay,
hence
all
the
right,
taping.
Okay, got it. Yeah. So there was a student who's reading this book and reading a section on spectral sequences, and that raised some questions. So that's. But I have to say the approach given in Bott and Tu, the presentation given in Bott and Tu is similar to that of other authors. There are a variety of different ways to approach spectral sequences, and there are a variety of different expositions in the literature, but this is somewhat standard. This is similar to the exposition given in, for example, Hilton and Stambach, which is one of my favorite books on homological algebra. Then one of the differences is that Bott and Tu are doing everything in cohomology, and Hilton and Stambach tend to do everything in homology, but that's not a big deal. You just change the direction of all the arrows. And Hilton and Stambach's presentation is a little bit more general, but otherwise it's similar. All right, so I'll refer to this a few times during the talk, and so if you've seen it, you'll know what I'm talking about. If you haven't, it doesn't matter. Okay, all right. Does anybody have any questions so far?
I just want to make sure this is the right. Have it a moment, just make sure it's the right. Holding a book, I think it's.
Oh, okay. Well, there's the one. That's it.
Well, the other one.
The other one. Oh, Hilton's. Hilton and Stambach. Oh, there's only one.
Oh, there's only
Hilton
one.
and Stambach that I'm aware of. Do I have any chalk?
Yeah, it's in my bag.
Okay.
I brought it here.
I think
Here you are.
Found a little. Oh, great. Okay. All right. Oh, thank you. Okay. All right. Okay. So to start out, I'm going to start with a very general concept, that of an exact couple. So I won't give a definition of spectral sequences right now, but I'll give a definition of an exact couple. And I think it's fair to say that almost all spectral sequences come from an exact couple. Maybe not all, but any one I've ever seen. All right, so this is going to be very abstract, but hopefully as we go along, it'll start to concretize and make a little more sense. Okay, so an exact couple is a diagram of abelian groups, like so. We have two abelian groups, D and E, and then we have three maps. I is an endomorphism of D, and then here's J, and here's K. And it's exact, meaning that I followed by J is the same thing as J followed by K. Okay, I followed by J is the same thing as J followed by K, which is the same thing as K followed by I, which is 0. All right, so because of actually, it's more than this. We have. Right. Okay. So what we want to do is define a map from E to itself, and D is going to be defined by K followed by J. All right. So I'm taking an element in E and I'm applying K to it to get an element in D, and then I'm just thinking of that element as sitting over here, and I'm applying J. So I is not involved. But notice that D squared is jk, and j followed by k is 0. So D is a differential on E. So we can form the homology.
Sorry, but were you assuming these are exact too, or it's just that those compositions are zero?
Well, this is an exact couple, so I'm assuming they're exact. So I mean more than that. I mean, this is true, but I mean it's actually exact. All right, so we can form the homology of E with respect to D. All right, now, okay, so far, that's it. So now what we can do is, given this, we can define something called the derived couple.
And none of these are graded, it's just.
I haven't, okay, right. So I haven't said anything about gradings yet. So none of these are graded, but I'm about to, very soon I'm going to suppose that there are graded. In practice, when you have an exact couple, the groups involved tend to be graded. Typically, not always, but typically they're graded. Oftentimes they're bigraded, oftentimes they're trigraded. So in this business of spectral sequences, there are usually lots of gradings floating around, and you want to pay attention to the bi-degree or the tri-degree of the maps. And the grading is important, actually. It's you use it to make calculations. But at the moment, nothing's graded yet. I'm going to define another exact couple, which I'll denote by D prime and E prime, and I'll call this I prime, J prime, and K prime. And so D prime, by definition, is just going to be I of D. And E prime, by definition, is going to be the homology of D. This is the homology of D with respect to that differential that I defined over there.
Homology of E, your homology of E. You said homology of D.
The homology, I'm sorry, the homology of E, excuse me, the homology of E using this differential that I defined, which is, I'm denoting by little d. Okay, so that's D prime and E prime, and then I prime is just going to be induced by I, so that's just going to be I restricted to D prime. And J prime is going to be defined as follows. We choose an element I of x in D prime. So J prime on this element I of x is going to be the homology class of J of x. I'll use a bar to denote the homology class. So if I have an element, if I have an element in E and it's a cocycle, the D of that element is 0, then it represents an element in the homology group or cohomology group. And so I'll denote that by a bar. So that's the definition of J prime. And you can check that it's well defined. I'll say a little bit about that in a second. But that's J prime. And then K prime is defined as follows. If I have an element in E prime, by definition, that's the homology class of some cycle X. So K prime is just going to be obtained by taking K of X. Okay, so now we come to your first homework problem. Check that everything is well defined. So there's a couple things to check there. And 2, verify that this is also exact. All right, so it's none of these things are hard. It's a little bit time consuming, it'll take a couple of minutes, because there's a number of things you have to check. In particular, to check the exactness of that, you have exactness at 3 spots, and each spot entails saying that a kernel equals an image. So you have 6 different inclusions that you have to verify. So you just write out, you can just do it. We're in the category of abelian group, so you can just do it element-wise. This is actually working in the abelian category. Never mind that. And so just check exactness at each point. And for well-definedness, you know, what's involved here. For example, this homology class is represented by a cycle X, but it could be represented by some other cycle X. So you have to show that the result is independent of the cycle you choose to represent the homology class. And furthermore, if X is a cycle, then you need to verify that K of X actually lies not just in D, but in I of D. But those things are all practically obvious. All right, so given an exact couple, that we form the derived couple. Okay, so then we can just keep on going. Now just rinse and repeat. So let's call the original exact couple. Let's call this D1, and then let's call the derived couple. Let's call the derived couple D2 and E2, and so on. So we get ER and DR. So we get a sequence of exact couples, each one derived from the previous one. So by definition, the homology of ER with respect to its differential is ER plus 1. This, in turn, it turns out, is the definition of a spectral sequence. A spectral sequence, by definition, is a sequence of differential abelian groups with the property that each one is equal to the homology of the preceding one. Okay, that definition by itself is so general that it's not that useful, but that's what a spectral sequence is. But starting with an exact couple, we iterate this process and we get a sequence of exact couples, and each one's the homology of the preceding one, so it's a spectral sequence, and so that's it.
Let's see, so the extra thing that this is added is this D and a factorization of your differential.
I'm sorry.
I'm just saying that the spectral sequence, as you said, was just E and D. Was spectral sequence, as you said, abstractly defined by E and its differential. But with the exact couple, the extra thing you've added was this D.
The spectral sequence, this is an exact couple. The spectral sequence is this sequence of groups, E1, E2, E3, each with their differentials, and each one being the homology of the preceding one. That's the.
But what I'm saying is the exact couple, what you've added to that is, in addition, you've added this capital D.
Oh, yeah.
And
okay.
the way of factorizing the differential.
Yeah, oh, yeah, right,
as a
right.
product of
Yeah, that's correct.
You need to say which homology, well, each is a homology of the preceding one, that leaves open the question, well, homology with regards to what? And then by having the D's, you're sort of carrying through some notion of what homology is with regards to it each step as well.
Yeah, right. Also, I agree with that too. I mean, the way I would say it is, I would just say, where do spectral sequences come from? Why would you ever consider such a thing? And the answer is they come out of exact couples. Exact couples occur in nature, and they give you spectral sequences.
Other spectral sequences and other planets.
Okay. All right. So this would be a natural stopping place. Are there any questions?
Now you know everything about spectral sequences.
Yeah. Everything. Well, you can pretty much deduce the rest from this. I mean, that's what I'm. Just sort of an extended exercise
Well, right.
with a lot of diagram chasing.
Well, it's all homological algebra, so just.
The parallel.
Yeah, there is. There is an exercise. There is an exercise in Lang's algebra book, which you're probably familiar with. It's famous. Lang has a classic graduate text in algebra, and there's a chapter titled Homological Algebra, and it's pretty short, which reflects his level of interest in the subject. And at the end of the chapter, the very brief chapter, there's only one exercise, and it says, quote, pick up any book on homological algebra and do all the proofs in that book without looking at the book. So, all right.
Yeah, attitude.
So, yeah, so, okay, moving along, all right.
So is this
yeah.
just a concise way of defining what a spectral sequence is, or is it that the examples actually never arise this way as like?
The examples arise this way. We're going to specialize to something called a filtered chain complex. And a filtered chain complex gives you an exact couple. So this is a sort of concise way to see how the filtered chain complex is giving you an exact couple and hence a spectral sequence. So it's just a kind of a concise way to sort of organize it. But it turns out that really what you want to do is sort of take the thing and explode it into a big diagram that you're going to chase through, and I'll do that in a few minutes. And I like to call that an unraveled exact couple. So we're going to put a grading on this thing, and then you can just think of it as a giant thing that's been very tightly coiled up into a little thing. And what we're going to do is snip it, and it's going to spring open into
Would it be all right if I went to get a cup of coffee? Would you be offended by it?
Really.
I really need a cup of coffee.
You need more than that, but all right.
Wait a minute.
Okay, all right. So all right. So how do you get exact couples? Well, one way you get exact couples is from something called a filtered chain complex. All right. So not every exact couple arises from a filtered chain complex. But many do. Oftentimes they do. And in the example, if we get to an example, it certainly will. So, all right. So what's a filtered chain complex? All right. So K is going to be a chain complex with some differential. I still haven't put a grading on anything yet. Still haven't put a grading on anything. So K is so actually wait, so let me, in fact, without a grading, we don't normally call this a chain complex. We just call this a differential abelian group. So it's just an abelian group with an endomorphism like so. All right, and then you can take homology of that. So a filtration on K is a sequence of sub-differential groups. So we have K, which I'll call K0, and then this contains K1, and this contains K2, and so on like that. And so this is what we would call a decreasing filtration. One could also consider an increasing filtration or a combination of the two, decreasing and you could go off in either direction. Let's just start at the top and consider a decreasing filtration. And so each one of these, each case of P is a subcomplex. So D restricts the case of P to give a differential on case of P. Okay, so that's what we mean by a filtered differential abelian group. Okay, now a filtered differential abelian group gives you an exact couple, and that in turn gives you a spectral sequence, and that's not too hard to see. So let's do that next. So that's one common way we get exact couples. Before I do that though, I'm gonna put a grading on K. Because that's a little bit more common. I mean, it's a little unusual. I should never say never, but it's a little unusual to encounter an ungraded exact couple. More commonly, these things have gradings on them. So let's just put the grading on it right now so that it will kind of look a little more familiar. All right, so K is actually going to be a chain complex. I'll suppose that K is a chain complex, and I'm taking a differential that goes up in degree, so I'll use a superscript. And so K is a chain complex, and when we take cohomology with respect to this differential, we get a graded abelian group because we have cohomology in each degree or dimension. I'll use the terms dimension and degree interchangeably. Okay, now I'm supposing that K is filtered, and so I have the filtration on this thing, and I'm going to use the superscript for the degree or the dimension, and the subscript for the filtration. I'm sorry, what's that?
Nothing.
Oh, okay. All right. So, and let's see. Oh, and let me mention, I am following at the moment. I'm following the notation of Bott and Tu pretty carefully. Bott and Tu use A's and D's instead of D's and E's. I switched into D's and E's because I'm more used to that. It's not really an issue until we get to a certain differential that Bott and Tu denote by capital D, and so then I'm going to have to call it something else. But we're not quite to that point yet. All right, so we have this. So we have this filtered chain complex, like so. And so now let's look at the direct sum over all P of these subcomplexes, and we'll call that D. And we'll look at the direct sum over all P of these quotient complexes, and we'll call that E, and that's our exact couple. Because, of course, let's see, it's a decreasing complex, because this is exact.
Sorry, can I ask a basic question?
Yes.
Okay, so when you move from a differential abelian group to a chain complex, because you already have your K and your D there, and is really just the condition that not only D be, nil square, but also that it be exact? Like, is that the only difference between?
It's,
Yes.
well, these are exact.
But I was saying, so if I have a K and a D, and for a differential abelian group, you're just asking that D be nil square, right? Not exact?
But D, this,
Right,
D is just D squared.
What, back there.
This is not exact.
So, okay.
This is not exact.
Okay, so what I want to understand.
This is just a chain complex.
Is you started on the left with the differential abelian group, and then you said, now we're gonna assume it's a chain complex.
Well, by that I just meant I didn't put a grading on this yet.
Right,
Then
and what I was wondering is, once you have a K,
I put a grading on it.
but you've got your K, you've got your D,
Uh-huh.
so the only thing missing to have it grading is just to pick some point, right, to be where you start, because then the D can generate the grading for you, or am I missing?
No.
Okay, sorry, this is why it's basic.
Yeah, no. D isn't generating. No, D isn't generating the grading.
Okay.
I could have an ungraded. I could have it. Here, you could do the following. Take a chain complex that you're familiar with, like the Durand complex for a smooth manifold, or the complex of singular cochains on a topological space, or just take your favorite chain complex of abelian groups. You could just forget the dimension, and then you would get a differential,
I see.
an ungraded. Forget the grading or the
Okay.
dimension, and then you get an ungraded thing.
So sort of like in the round case where he said we just imagine formally taking things like sums of differential forms of all orders,
Right.
as sometimes people
Right,
do,
and I
and
don't-
these
yeah,
still
exact-
act
right,
order by
right.
order.
Right, yeah. So you could just forget the grading to get an ungraded thing. I'm just saying, suppose we have a grading. I
Okay.
just want to suppose there's a grading on it. So the grading and the filtration don't have much to do with each other, except that I'm assuming that the subcomplexes, so the filtration consists of subcomplexes, and I'm just assuming that they have the same grading. So for example, I wasn't gonna write this, but you could write this, for example. If you wanted to say that. Okay, yes.
So by this star, you just mean you're taking the whole complex? That's all star means?
Oh, yeah, star, if I write star, it just means there's a grading there, but I'm not paying attention
You have like
to
two
it.
direct sums?
Yeah, it's like the,
I don't know.
yes, actually, that's probably a better way to,
And I guess likewise on this.
What's that?
And likewise with.
Yeah, likewise over here. I would support that. Okay, so we have a filtered chain complex, but now those sequences are all exact. So this is an exact couple if you think of it. I mean, so the I, for example, is just inclusion, right? Because the direct sum of the KPs includes into the direct sum of the KPs, because KP plus 1 sits inside of KP. So I is just inclusion, and J is just, well, actually, let's see, hang on a second. Hold on just a second. I don't have an exact couple. I have an exact sequence. I don't have an exact couple yet. This is an exact sequence by definition. I don't have an exact couple yet. So let me get the exact couple. So we want to get an exact couple, and hence the spectral sequence of it. So these things would, I guess, could be called D naught and E naught, but this is not an exact couple yet, right? Because I don't have a K, right? I don't have anything going from there to there, so I don't have the K yet, right? Okay. So now I think I just want to draw the big diagram.
So what are the I and J? Can you explain that again?
It's not yet.
Well,
Yes, I indeed.
Not yet.
Just not
well,
K.
there's an I and a J here. There's an I and a J here, so they're gonna induce the I and J of the
The
example.
problem is now you've got zeros on the end instead of it looping back on it.
Can we
What's that?
write the I
You've
and
got
J
zeros on the
that
end
arrow?
here. In this chain, you have zeros
Yeah.
instead of looping back on itself.
Yeah, I do. Well, this is yeah. I don't have a map from there to there. This is just a short exact sequence.
Couldn't you just declare K to be the zero map and then you have an exact couple?
Can we write the I and the J on there?
Guess it doesn't
Well,
matter.
but you
Well-
want the K to give you back the D, you start something interesting.
Well, hang on a second. We could, except then when we get the E1, the K in E1 isn't going to be induced by the K in E0.
Okay.
So that's a sort of. I mean, yes, you could, but that
Yeah.
that would be an
Doesn't work.
artificial thing. This is not an exact couple yet. I mean, you
Okay,
don't have an
all right.
exact couple
No,
yet.
yeah, you wanna put
I-
the D to use somewhere.
Yeah, okay.
I mean, if you're taking the J from this sequence, then the K has to be 0, doesn't it? If you want exactness?
I don't want, I'm not trying to get an exact couple.
Okay.
I have an exact sequence. I don't have an exact couple yet. So that's all. So I'm not thinking about a K.
I'm not
If I can
convinced
make
by what you said. You said I is just that map and J is that.
Let
map.
me just retract.
Okay.
That was a misspeak. All I meant to say. Here's what I meant to say. I meant to say that this is an exact sequence. That's all I meant to say. For each P, we have an exact sequence of graded abelian groups. That's all I meant to say. Anything else I said was erroneous in extremes.
If I could make a comment
Sure.
relevant to these questions, that is in some sense a degenerate exact couple where the K is 0.
Okay.
So all the differentials are 0 and all the E's are the same, so it's the degenerate spectral sequence would come out of that if you wish.
Okay.
To make them happy.
Okay.
Not to say degenerated makes them happy, but,
Okay.
I just wanted to say that.
I really do not want to endorse the
Yes, I do.
effort to think of this as an exact.
You're right. I just was trying to make them happy.
Okay, so what I want to do is I want to look at the long exact sequence in cohomology. So let's see. I have to try to sort of. I like to try to space this thing so I don't run out of room. Okay, so I'll have KP there, and then this will go to HN of KP mod KP plus 1. And then this is going to boundary around to HN plus 1 of KP plus 1. And then I have HN plus 1 of KP, HN plus 1 of KP, KP plus 1, HN plus 2 of KP. So what I'm doing is I'm writing down the long exact sequence in cohomology that comes from that short exact sequence of chain complexes, and you get the long exact sequence in cohomology by the Jill-Clayburgh lemma. The Jill-Clayburgh lemma is sometimes referred to as the serpent lemma or the snake lemma, but I like to call it the Jill-Clayburgh lemma in honor of the fact that Jill Clayburgh, who was a wonderful movie actress from the 60s and 70s, who played a mathematician in a movie called It's My Turn. And I strongly recommend the movie. And the first scene in the movie, and when I say the first scene, I mean literally, it's the opening scene with the credits rolling. So you have to watch right away. But she's giving a lecture, and she proves the serpent lemma. And so it's a marvelous thing to see algebraic topology being proved in a Hollywood film starring a popular Hollywood actress. And what's more, the film was shot in New York and takes place in New York. And Jill Clayburgh came to the math department at the Graduate Center and was coached by the local mathematicians in the department here. Al Vasquez, who is not at the Graduate Center anymore, he retired, but Al and several other people coached her on this, and they did a marvelous job, and she did a marvelous job, and I recommend you watch it.
So does that mean we have to start
Okay.
saying our announcements to actors now?
Yes, yeah, we should actually put the movie people on our seminar mailing list. Martin, you can get right on that.
She was going to get an Oscar for that.
What's that?
There was an Oscar that she almost got for that.
Yeah, she was nominated for an Academy Award.
But had she gotten the lemma right,
Her research was on something in group theory. She was studying some group, and throughout the movie, there's this line that gets repeated several times where her boyfriend or her husband or one of her co-stars would say to her, "So how's your group?" And she'd say, "Oh, it's good." So anyway, all right. So I'm writing out the long exact sequence. Hopefully, let's see. Hopefully not
And
not
shouldn't that
messing
be
it
K
up.
plus, P plus 1?
And there's a reason that I'm writing it out in this zigzaggy way instead of. Let's see. Do I have this right? So I
That's
have-
KP plus 1.
Yeah. Okay. So let me try to get this right.
you don't have the quotient going to the.
Yeah, or you won't get an
Yeah,
Oscar.
okay. Yeah. I'm not trying for that. But okay. So KP minus 1. KP plus 1. So here's n plus 1, n plus 1, n plus 1, n plus 2, so on.
That should
I
be
have
good.
P plus 1P, the quotient, P plus 1P, the quotient. Yeah, okay, this looks okay.
The top right. Should be a KP plus one.
Let's see, thanks, okay. All right, anything else? Okay, all right, so that's one of them, but there's one of these for every P. Okay, so if I look at the next one, this would be KP minus one, going to HN of KP minus one KP, like so, and then I have HN plus one KP minus one. So, HN plus one KP minus one mod KP, and so minus one KP minus one KP, and so on. Let's see here. Let me just put a couple. I'll just put a couple more. You can see the pattern. Okay, and so you have this giant diagram, and then what I like to do is just put, just kind of indicate, just to sort of indicate how we're making our way through this thing. Right, so that red indicates the long exact sequence for the P thing, and then I have the P minus first thing above that, and the P plus first thing below that. And so now this is an exact couple. This is an exact couple. The E's are the cohomology of the KP's. The cohomology of the quotients, those are the E's, and the D's are the cohomology of the KP's. So another way to describe an exact couple, or a way to get an exact couple in the graded case, another way to describe it is whenever you have a sequence of long exact sequences that hook together, that sort of hook together in this fashion. So the sequence of long exact sequences where 2 out of the 3 terms of each sequence are shared by the adjacent sequences. So I have a long exact sequence, and 1 out of every 3 groups also belongs to the next long exact sequence, and 1 out of every 3 groups belongs to the previous long exact sequence, and every one of the long exact sequences has one term, every 3 spots. There's one term that doesn't belong to the other ones, and that's a description of maybe not a general exact couple, but that's a description of the exact couple that comes out of a filtered complex. And
so Rob, those things were not used then. Those right there, right on this board.
Yeah,
You wrote this
yeah,
direct
yeah.
sum.
Those were exactly. Those were not used. Okay, so this is a good way. So the reason I like this picture is because it enables you now to sort of see what's going on. So you'll notice, or start to see what's going on. So you'll notice that you have these sort of towers here. See, I've got a decrease in filtration. So sort of sitting up at the top, not exactly, well, actually, since this is a decreasing filtration that started at 0, in fact, this will equal that as soon as I get down to 0, right? Case of 0 is K. So I do have the cohomology of K sitting up at the top. I have an HN plus 1 of K sitting up at the top there. And so you can see the towers. And now we can describe the different. Okay, so now let's see, let's put in some things. So these are the I's. These vertical homomorphisms are the I's. And these horizontal things, these are the J's. And these are the K's. So the K is the boundary homomorphism in the long exact sequence that we got from the Serpent lemma. Is that, oh, you're just, yeah, right, yeah, I do that too, yeah.
It's exact.
This is what you do all, for a long time, you spend a lot, many hours.
That are walking on the street.
Okay, so let's see, we can just, let's describe the differential, which is, of course, it's K followed by J. So in this picture, let me use a different color here. So I'll use a green for the differential. So this is the E1 term here, or okay, this is the E1 term. So this is the differential. That composite is that composite is the first differential, the D1. Now you can sort of use this picture to describe the second differential. So let's say that I had here, I'll go down to here. Let's say I had an element in E1 in this spot, and I did D1 on it, and I got 0. Okay, so in the spectral sequence, if I have something in the E1 term and D1 is 0, then that's a cycle, so that represents a homology class, so that represents something in E2. All right, so what would it be? Well, if I have an element here and D1 on it is 0, then that means that this mapped to something which, or I'm sorry, let me go up here. So I have an element here, and I do D1 on it, and it goes to 0. That meant that K on this element here was in the kernel of J, and this is exact, so something in the kernel of J is in the image of I. So I would take that element that I got here, and I would pull it down to there, and then I would map it over to there, and I end up getting a map going from here down to here, or from subquotients of those things anyway. But this is essentially the D2 in this diagram. And if D2 on something was 0, then I would take the thing that I got here and I'd pull it down one farther, and I would map it over to there, and then that would represent the D3, and so on. So this is all modulo a lot of indeterminacy, because really when you get to the E2 term and the E3 term and so on, you're dealing with subquotients of everything in sight. But you can nevertheless trace out the differential in this diagram, which is helpful for making calculations and kind of proving things about what's going on. Okay. All right. Okay. Does anybody? Okay. I hope there aren't typos in that. Does anybody have any questions about this? Filtered complex gave us an exact couple, which I chose to draw out as a big array, just to kind of get a better look at it.
Why don't people write textbook in this way?
Why don't people
Write textbook in this way?
Why don't people write textbooks? I don't really know how to answer that. I don't know. Well, I'm not sure what you mean by in this way. It's hard to.
Is that picture in any book?
Yeah, maybe that's the picture.
Yes.
Oh,
Yes, it is.
In the
Yes, it
Cleary's
is.
book, for example, it's in the Cleary's book.
You know what? I love John, and he's a dear friend of mine, and I've known him for many years, and I've never really read his book. It's a sin of omission there, because I've heard nothing but great things about it, but I'm not actually familiar with it. I mean, I've glanced at it, but yes, Mosher and Tangora write this diagram when they're doing the stereospectral sequence.
Right.
And Mosher and Tangora, by the way, is an excellent book, and it's really, I think it's a great introduction to homotopy theory and fiber bundles and fibrations, and Serre's method of using the stereospectral sequence to compute homotopy groups. And so when they do the stereospectral sequence, yeah, they write this out. Let's see. Now I have to give a caveat. If you do study Mosher and Tangora, which I strongly recommend, when you get near the end of the book and they start doing stable homotopy theory, just stop. Don't do it. Just don't even look at it. Not worth it. Just go to Adams or Switzer or
Right.
May or somewhere else. But the unstable stuff is really great. Oh, and by the way, people say, I believe it's true, that much of Mosher and Tangora, a lot of Mosher and Tangora is due to Frank Peterson. So that should be noted.
How so?
What's that?
How so? He gave lectures?
Frank Peterson did a lot of things, but so one of the things he did was Frank Peterson studied Postnikov towers and Eilenberg McLean spaces, and he studied the cohomology of Postnikov towers, and he got invariants for topological spaces looking at the cohomology of Postnikov towers. That was one of his main areas of research, and that led to all kinds of things, not the least of which is the Brown-Peterson spectrum, because Brown and Peterson produced the Brown-Peterson spectrum originally by building a Postnikov tower. So that all came out of Peterson's work. So yes.
The D3, it goes over two spots, right, when you pull it down, and I don't know if it's.
Let's see, okay, all right, maybe, let's see if I said this right. So D1 goes across, D2 goes over and down, D3 would go,
No, one more.
One more, right?
One more to the right.
What he said was correct.
no, it's not one more to the right. No, you're thinking of something else.
Oh, yeah, no.
You're thinking,
no,
I know what you're thinking of.
Okay.
You're thinking of a different diagram, which I haven't drawn.
Okay, no.
Yeah,
No, they all go.
They all end
go.
on that.
Yeah.
They all go from here to here, but
Yeah.
just farther and farther down.
Yeah.
Yeah, you're thinking of it.
Oh, yeah, I got it.
What is infinity?
Oh, well, okay, thank you.
Nothing was
Because that's where we want to go now. Okay, so now, let's see, moving forward, now the next thing we want to do is we want to say something about what this is getting us. What is this for? Or just, to use a little spectral sequence lingo. I'll say, what is the target of the spectral sequence? There's a lot of lingo in the subject of spectral sequences, and much of it is very violent. You talk about, when you compute the differentials, you talk about this element kills that element, and this element dies, and you say, well, this element dies at the E2 term, and you say, well, this element survived to ER, but then it died at ER plus 1. And Joel Cohen was a homotopy theorist who was studying the atom spectral sequence, and he formulated this conjecture about stable homotopy groups of spheres, which I won't go into right now, but I'll just say that he formulated this conjecture based on his study of the atom spectral sequence, and in order for his conjecture to be true, it meant there had to be a massive number of differentials, sort of killing almost everything off. So when Michael Barrett heard this conjecture, he said, oh, well, we should call that the doomsday conjecture. So that became known as the doomsday conjecture. It turned out to not be true, but if you ever hear about the doomsday conjecture, that's the reason why it's called that. Very violent subject.
E and D here are chain complexes. Or are we just looking at them as abelian groups? Oh, no.
That was a typo.
Could it be violent because it was developed in a prisoner of war camp?
Well, not just any person, right.
Okay, yeah, perhaps, yes. Martin is referring to the fact, so since we're giving little historic, fun facts from history, Martin is referring to the fact that most people credit the original conception of the spectral sequence to Leray, and Leray came up with the idea when he was sitting in prison. So.
Well, not just any prison,
Yeah.
a Nazi prisoner of war camp in World War II.
Right. So he,
Not
yeah,
just
so, yeah,
prison.
right, so he, yeah, so Leray was a French mathematician who was in prison for a good part of World War II, and so he's just sitting in his jail cell, and, you know,
What do you do?
yeah, I mean, I mean, most of us, all of us, or some of us, can't conceive of what that would be like, but you just imagine, you know, what would you possibly do to keep your mind occupied? So he came up with spectral sequences. Yeah, good. All right.
Yeah, so in Sayre's original paper, he also decomposed the differential operator in terms of P and R. So he also counts the differential operator sending the P abelian group to the KPN to KPN plus R. So so this method is much simpler than Sayre's original paper. Can you understand this result comes from the exact couple?
Yeah.
Yeah, so by the exact couple, we don't have to decompose the differential operator in terms of P and R.
All right, so the by original paper, you're referring to Loray's original paper?
Sayre's original paper.
Oh, Sarah's original paper, right. Oh, so I haven't actually read Sarah's paper, but I think I believe you're right that you're saying that Sarah does not
So we
use
use
exact
exact
couples. He's not formulating things in terms of exact couples. Yeah, I think that's correct. The concept of the exact
formula
couple.
Will be much more.
Came-
That was
came later.
was not a PNAS paper?
I'm not sure.
Something like that.
I'm not sure where that first arose, but you're right, the concept of an exact couple as a way of formulating the spectral sequence came along a little bit later. I wouldn't be surprised if Moore had something to do with it.
I thought Massey developed.
Or Massey,
Massey,
okay,
that
all right, well, okay.
But
Shows how much I
he's
know.
also asking, I think, if that can be obtained using this
Yeah, so if Sayre's formulation
Sayre's
can be obtained
spectral
from
sequence.
Oh,
can it-
yes, well, yeah, we're gonna,
He's gonna do that. I
yeah, we're
think.
gonna write that down in a minute, yes. Yeah, we're gonna write that down in a minute. Let's see, the other comment I was gonna make though is, if this looks a little bit simpler than some of these extremely long, complicated expositions that you've seen in some books, that's because, I'm just sweeping a lot of stuff under the rug, okay? I'm not, this is just a picture to kind of guide you, but I'm not, I haven't, I'm about to make some statements that require proof, and to give a careful proof, you have to chase through a lot of definitions and write down a lot of steps, and by the time you're done, you're gonna have the same, multi-page, long-winded exposition that you see in all the books. So don't think you're gonna run out and write your own book that's gonna be simpler than everyone else's, because it'll end up looking the same. Okay,
That way, it's historical creators. Massey in 1951 came out with the exact couple.
good, thank you. Yes, that rings a bell.
It was Annals
Okay.
of Math.
Yeah, okay, oh, all right, 51, all right. Did you say
Much later,
51?
yes.
Well, that wouldn't have been much later. That actually,
Well, but at least 5 years later.
Oh, 5. When did Sarah write,
when was Sarah's thesis? I thought Sarah's thesis was in the 50s.
Oh, I don't know.
yeah, I'm a little confused.
Yeah,
But, you
Well,
know,
exact couples, yeah.
all right, well, okay, anyway, all right, let's move on. All right, the history's fun until you start getting it wrong. Okay, so, all right, so the point of this, the point of this, as you can imagine though, is we're trying to compute the cohomology of K. That's sort of the goal of all this. And so how is this going to do that? Well, recall that we have, I'll just write this down again. K is filtered. K is filtered like so. So when we take cohomology of these chain complexes and their subcomplexes, then we get a sequence of cohomology groups like this. You can imagine everything's graded, but I'm just suppressing that now. But anyway, so you have a sequence like this, and of course, you know, these are no longer necessarily injections, right? Because the cohomology of an injection typically is not an injection. So these are just maps, but they allow us to define a filtration on the cohomology of K. This is the cohomology of K. So we get a filtration on the cohomology of K defined as the image of the map from the Kth subcomplex. All right, so if we take the image in here of the cohomology coming from the Pth, I meant to say Pth, the Pth complex, then that gives a subgroup of that. And this is a filtration, on the cohomology of K. And it's a decreasing filtration, of course. It came from a decreasing filtration, and it is itself a decreasing filtration. This is F1, and so on. And then we can form the associate, what we call the, given a filtration on a abelian group, we can take the subquotients of the filtration and we get a graded abelian group, and we call that the associated graded. That's sort of short for the graded group associated to the filtration. But we usually just say the associated graded. So we have this giant direct sum of all the FPs. All right, so what the spectral sequence is going to try to do is it's going to try to converge, what we call converge, to the cohomology of K. But what really it's going to do, it's a device which is going to.
Do you mean FP mod FP, a quotient? there?
Yes, I did, in fact, mean that. The FPs are the filtration, and then I take the filtration quotients to get the associated grade. Thank you. Okay, so, all right, so the idea is that this thing is some big computational device, and we want to get some kind of succinct description of the input and some sort of succinct description of the output. All right, so let's not worry about the first thing right now. What's the time, Mahmoud?
So the next talk is at 2, so we said we stop
So
at
1:30, the target, 1:30-ish is the
Yeah.
goal, right? Okay, 1:30-ish is the goal. All right, okay. So, all right, so let's not deal with the description of the input yet. We'll get to that, I think. We'll wait until we refine this a little bit further, or specialize this a little further. But we can just start talking about the output. So if this thing works, then this is what should come out of it as the output of the spectral sequence, is the associated graded object to this filtration on the cohomology of K. Now, if you want to know exactly what the cohomology of K is, and all you've got is the associated graded of this filtration, then that means you've got a bunch of extension problems that you have to solve, right? You have FP and FP plus 1, and you have their quotient, and if you know the quotient, then you have to somehow try to recover the sub-objects in the filtration from that. And so that's called the extension problem, and the spectral sequence doesn't help you with that. That's sort of outside of the purview of the spectral sequence itself. The most that you can expect to get from the spectral sequence would be the associated graded. Now, of course, let me just point out though, let's say you're applying this to something like de Rham cohomology, and so everything in sight is a real vector space, and at least as far as the additive structure is concerned, the only invariant of a real vector space is its dimension, and everything's free because you're looking at vector spaces. So if you have the associated graded objects, which are real vector spaces, then you immediately recover the this thing, at least as a graded real vector space. So in certain cases, the extension problem is easy to solve, but then in other cases, like if you were just dealing with abelian groups, let's say not necessarily vector spaces, even if they were finitely generated abelian groups, you know, the extension problem could be difficult. You know, if FP is a Z2, and if FP mod FP plus 1 is a Z2, then what's FP plus 1? Is it Z2 direct sum Z2, or is it Z mod 4? You know, that's
But I
an
can
extension
work
problem.
over vector space. I can deal with vector spaces over a finite field too, and the same thing works.
Yes, yeah, absolutely, yeah. If you were doing singular cohomology, but it had coefficients in FP, the field with P elements in it, then you'd know, you wouldn't have any extension problems as FP modules. Absolutely, right, okay. But anyway, so now just let's sort of quickly kind of see how this happens. I'm not gonna do this rigorously, but let's just suppose, so this is something that they do in Bott and Tu, so just to kind of help you see what's going on. Suppose that the filtration is finite. So let's say K was K naught, containing K1, all the way down to some KP, and then let's say KP plus 1 is 0. And everything from P plus 1 onward is 0. So let's say you had a finite filtration. Okay, then it's not too hard to sort of see what would happen here. These vertical towers going up, they terminate at the top, of course, because when you get to 0, you're at K. But they would also terminate down at the bottom. So every one of these towers would be finite. And then you can just sort of see, you know, if I have an element in the E1 term and D1 on it, let's say I have, here, let me go over here. Let's say I have an element in the E1 term and D1 on it is 0. All right, so then I do D2 on it. Let's say that's 0. I do D3 on it. Let's say that's 0. Eventually, I'm going to get down to 0. So for some sufficiently large R, dr on that element is going to be 0. And so that means that I got some element in one of these groups that mapped to 0. So let's see, wait, where did I start? I started, I lost my place here. Okay, yeah, suppose I went from here to here, right? So then eventually that means that I pulled this all the way back to 0. So I got something that was 0. So that meant that in this tower, let's say it was here. Let's say it's 0 here. So then this element is actually 0. So that means that so what am I trying to say here? Then the original element, okay, I started here, so then the original element here, if it pulls back to 0, that means it's 0. So it's in the kernel of K, so it pulls back by J to something here, and then I just shoot that up into K, and that gives me an element in K. So that means that any permanent cycle, what we call a permanent cycle in the spectral sequence is a permanent cycle in the spectral sequence is an element such that all the differentials on it are 0. So D1 on it is 0, D2 on it is 0, D3 on it is 0, etc. So you can just see from this diagram that if you have a permanent cycle, then that would give you an element in the cohomology of K. And then conversely, if you have an element in the cohomology of K, then you pull that back as far as it goes. It's going to come back to somewhere in this tower because we're assuming the filtration is finite, so it can't go all the way back. If it's non-zero, it's going to come back somewhere in the tower. So then if I just map that over here, that'll give me a permanent cycle. So basically, you get a one-to-one correspondence between the elements in the cohomology of K and the so-called permanent cycles. This is all assuming that the filtration is finite. So let me just write that down. So what happens is in the exact couple under this finite filtration hypothesis. So let's say KL is 0 if L is bigger than P. This would be a filtration of length P. we call this a filtration of length P. So then in the exact couple, what would happen is DL plus 1 would be the same as DL plus 2, would be the same as DL plus 3, etc. So these groups they all stabilize. After a finite number of steps, nothing further happens. So this stable limit here, I'll just call that D infinity, and this stable limit, I'll call that E infinity, and then our exact couple looks like, here, let me go over here. Our exact couple would look like this. Here's D infinity, E infinity, D infinity, and this I infinity is actually just inclusion, and J infinity is just a quotient map, and K infinity is just 0, and then we have a short exact sequence like so. D infinity includes into D infinity, and E infinity is the quotient. And then, if you just inspect it a little bit more, you'll see that this inclusion, when you take the quotient of D infinity by D infinity under this inclusion, you're just getting this. You're just getting this. So in fact, these E infinity groups, which are what you end up with after a finite number of steps, because the filtration was finite, these are in fact just the associated graded. So I'm kind of, sort of sloughing a little bit of the details under the carpet, but not really. I mean, I'm not writing everything out in detail, but it's just pretty easy to check that under this assumption that the filtration is finite, everything sort of, after a finite number of steps, everything just stabilizes or becomes stationary and stops changing, and you just end up with the so-called E infinity term, which is the associated graded. So
where does the permanent cycles fit in?
Okay, so I said that sort of fast. I didn't write it down. I'll say it again. A permanent cycle is an element. Well, I mean, it's really a whole bunch of elements, but just think of it as an element in the E1 term, which is a cycle under D1. Hence, it represents an element in the E2 term, and then that happens to be a cycle under D2. Hence, that represents an element in the E3 term, and so on ad nauseum. So it's just it's an element in the spectral sequence starting out in the E1 term that is just in the kernel of all the differentials. That's what we call a permanent cycle. And the E infinity term is generated by all these permanent cycles. Now you could have a permanent cycle that's hit by a differential at some stage, in which case it would be 0 in E infinity. But everything in E infinity is represented by a permanent cycle. And I'm pointing out that in this diagram, you can just chase through the diagram, and you can just see right away that every permanent cycle in the spectral sequence gives you an element in the cohomology of K, and vice versa.
But doesn't that contradict the fact that you said at best you can only get at the associated graded?
Well, no, I didn't. Well, maybe okay. So I didn't say. Okay. All I said was, if you have an element that's in the spectral sequence, which is a permanent cycle, so that represent that in E1 by some element in this group. The fact that it's a permanent cycle will lead you to get an element in here. So there's a map from E infinity to that. I didn't. Yeah. So what's the
Well, yes. I mean, up there is the cohomology of K, not the graded associated graded of the cohomology.
Right, but what you can see in the finite filtration hypothesis, what you can see is that the E infinity term is the associated graded. So you're getting so permanent cycles are representing elements in here, but the isomorphism is between the E infinity term, which is a subquotient of this, and the associated gradient of that.
Can I perhaps add
Yeah.
that what you're asking is where that element would appear in that direct sum, so.
Well, I'm just surprised that he is saying you can actually get your hands on the
Right.
elements of the cohomology, not the grade, associated graded.
Oh,
He's
yeah,
just
no,
saying that-
Not,
But he didn't say that, actually.
Well, it says just look.
So you get an element in the cohomology, but then it'll appear, let's say, suppose it appears in F3 mod F4 as a non-zero element. You'll just see it in that sense. So it also would appear, for example, since it's decreasing filtration, it'll appear in F5 and F6, but in F6 mod F7, it'll be zero. It only appears it appears first as a non-zero element where it's in the lowest filtration, and that's how you see it in the quotient.
What's the relationship between permanent cycles and this direct sum?
Right here. This is the theorem, this is the conclusion. This is the theorem.
Permanent cycles are elements of E infinity.
Right. Exactly.
Permanent cycles, represent elements in E infinity. E infinity is, technically, it's a quotient group. E infinity is a quotient group. It's permanent cycles, mod boundaries. You'll often see, this isn't part of this exposition, but you'll often see one way this is often done is you define a group of permanent cycles and you define a group of boundaries and you get an isomorphism like this.
So, but you said permanent cycles live in Hn of k.
I didn't mean, no, that's not what I said exactly.
Well, you said up there.
I didn't, okay. All right. We have this on tape, so I can't get out of this that quickly, and believe me, I'm no Corey Lewandowski. But what I just meant to say, sort of informally, I don't really mean this as a precise. This is the precise statement. This, under the assumption that the filtration is finite, these groups are readily seen to be well-defined. The differentials all become zero after a finite number of steps. And so E infinity is a well-defined thing. And the theorem is that E infinity is isomorphic to this associated graded object, which is also a well-defined thing. So that's the theorem. But
Well, I don't know if this helps as an example. Suppose the cohomology of K is Z, and your filtration is by powers of P, so an element will be an FP if it's divisible by P to the 2 to the n plus P is 2, different P, so 2. So you get an element, so all the associated gradients are Z mod 2s, a sum of Z mod 2s. So if he finds an element, suppose he finds an element which is 4, the element 4 shows up. It'll appear as an element, as one of the Z mod 2 is going to be the guy that's in degree 4. You'll see it in that way, uniquely in those sum of quotients. So Z would be broken up into a sum of Z mod 2s, and it's correct what he said, that it appears as an element in the cohomology of K, but where it'll appear uniquely in the associated graded in one of those groups. And to unravel exactly how that filtration is working, as he said, that's the extension problem. But it will give you a unique element in the associated graded. I don't know if that helps at all, but
yet another way to say the same thing that he said and what I've been trying to say, but in terms of this diagram that I, obviously am fond of, is think of it this way. Let's say that I have this element here in E1, and let's say it represents a permanent cycle. So all the differentials on it are going to be 0. So that implies that back in E1, if I apply K to it, I get 0. So it pulls back to here. So now I have an element here. Okay, so notice that this element here maps to an element in the cohomology of K, but it comes from here. So it's in filtration P. So it actually is an element in FP of the cohomology of K. And so if I then project that down to FP mod FP plus 1, I get an actual element in the associated graded. And then I can say that this permanent cycle represents that actual element. So that's this isomorphism that I'm stating here, but just a little bit more precisely in terms of this diagram. Is that
Well,
better?
not quite, because it seems that you already got to H n of k, so, I mean, why would you want to project it? You have something better than the projected.
But that's not what comes out of the
Well, the
spectral
theorem, the theorem
sequence.
isn't going to say, the theorem isn't going to say that the E infinity term is somehow the cohomology of K. And if I
No, no,
suggested that in any way, that's not what I meant to say. I was being a little more heuristic here. The theorem is that the E infinity term is isomorphic
no,
to
you did not
this
say
associated
that.
graded object.
I'm not accusing you
Yeah,
of saying
right,
that, but
okay, yeah.
I just want to see
But I'm just saying you
the
can
idea
just
of
kind of
permanent, when you find a permanent cycle, what have you found?
You
An
found,
element of cohomology of K or an element here?
well, you've found an element in here, which may or may not be zero. And if I have an element in here, then that sort of pulls back to an element in the cohomology of K, but not in a,
definedly,
what's that?
not in a well.
Not in a well-defined way, but
But the way you said it is well defined. You said it goes up.
But he started with
no,
an
but
arbitrary
there's
choice.
the
He started with an arbitrary choice of representation.
Yeah, but over there, you just followed those maps going up.
What he calls permanent cycles are just representatives of what you end up with in the infinity.
you know there's a non-uniqueness when I say pull the pullback also, remember.
Okay.
I said that you have an element in E1 here, and if it's a permanent cycle, it's going to go to 0 here. So it pulls back to here.
Okay,
But that's not unique.
okay. But the
Maybe
rest of
that's
it
the
is,
issue.
the rest of it is.
If I have,
Yeah.
okay, if I had a well-defined
Yeah,
element
fine, the
here,
arrows are
that
fine.
would give me a well-defined element
Okay.
here. I think that's your
Okay,
point. That's your point. That's your
okay.
point, which is a point well taken. When I pull back to here, that's not unique.
Okay,
I can just, there exists something in here.
okay, that explains.
Yeah. Okay. So
Right,
that's,
so the
yeah,
only
okay.
unique, right, so the only
Yeah.
uniqueness you get is that it's in somewhere in that direct sum.
Right, okay. But I want to emphasize though that this heuristic, non-well-defined, intuitive diagram chasing with the finger can actually be used to compute things, right? You can actually compute a differential with this. All right, so, okay, so now, all right, so does that sound, okay, all right. Okay, so now moving along, sadly, the filtrations that we deal with are rarely finite. Okay, so that's, I mean, they could be, but typically they're not. So saying that this thing converges and gives us an associated graded to the cohomology of K is well and good, but typically the filtration's not finite. So
You have to work harder.
yeah, so you have to work harder, but I'm going to state a theorem, and this is in Bott and Tu, and the proof of this theorem is not much harder than what we just said. It's maybe instead of 3 lines, it's maybe like 10 lines or something, but it's really not a big deal. So what we're going to do is we're just going to, and now I really do want to assume though that K is graded, because the grading is now going to play a role. So let's suppose, here's the theorem. Let I'll just say this is this gadget that we've been talking about. Let this be a graded, filtered differential abelian group. In other words, graded filtered chain complex. And then let's suppose that the filtration is finite in each dimension. So in other words, when you look at, if you fix a dimension K in, and you look at K in containing KN1 containing KN2 and so on. There's some P, possibly depending on N, for which this filtration has length P. All right, so the only difference between what I'm saying now and what I was saying a little bit before is that the length of the filtration might depend on N. Okay, but that's okay. As long as for each N, the filtration is finite. Then the spectral sequence converges. All right, so let's see. Then the resulting spectral sequence converges. What do I mean by converges? I mean, in other words, for each n, if I look in dimension n, then this thing stabilizes to some group this is for R large enough, depending on n. All right, and we get the desired conclusion that the infinity term is the associated gradient. Okay, so to prove this theorem, and I'm not going to go through the proof, but to prove this theorem, I mean, all you're really doing is you're just taking the argument that we sort of sketched, a little hand wavy, but we sort of sketched for the convergence in the case of a finite filtration, and then you're just sort of chasing through the diagram and observing that you can apply that argument in each dimension. As long as you have the finite filtration in each dimension, then the same thing happens, and you get the result. So there's a convergence. There's a convergence theorem, which is used all the time in practice. So for example, in the Serre spectral sequence, this is what's happening. Just to take an example. So convergence in the case of the Serre spectral sequence is not a subtle thing. Now, in other spectral sequences, the atom spectral sequence, for example, the convergence is a more subtle question. It's not that simple, but for something like the Serre spectral sequence, this is good enough.
So in the case of atoms, it may not necessarily, for each n, it may not necessarily.
Yeah, exactly.
And by FP, you mean FP of HK, right?
Yeah, and I just got tired of writing. Yeah, I meant FP of HK. Exactly. All right. So let's see. All right. So we don't have a lot of time left. We have a few more minutes. There was another thing I was going to say. Should I proceed and try to say another thing? Okay. All right. So I'll just try to sort of squeeze this in not too much time. All right. So I think I'm going to. Yeah. Okay. So I think I'm going to erase this diagram now. I don't think we need it. We'll pick up the next.
Did you take a picture?
Okay, so now let's just specialize further. We gave an arbitrary definition of a spectral sequence, which was too general to be useful. We said that if you have an exact couple, then that gives you a spectral sequence. That was still quite general. Then we said if you have a filter chain complex, then that gives you an exact couple. So that's a lot more specific. But now let's get a little more specific. Where do filter chain complexes come from? Well, one of the most common, a very common source of filter chain complexes is from something called a double complex. So many spectral sequences arise from a double complex. So let's just say what that is. Okay, and I'll have to I'll sort of go through this with a little bit of haste. But so a double complex is a bigraded abelian. I'm going to assume that it's non-negatively graded. So it's a bigraded abelian group. And there are two differentials. delta, which raises the first degree by 1, and d, which raises the second degree by 1. And I'm going to assume that these differentials commute with each other. And then from the double complex, we can form a single complex, which I'll denote by CK. And the definition of that is CK will be the direct sum over all P plus Q equals K of K P plus Q. And then we can put a differential on CK, which I'll call boundary. And it's going to be defined by taking delta plus minus 1 to the PD. And the sign is in there to make the boundary squared equal to 0 so that we do get a chain complex. All right, so a so a bigraded abelian group, two differentials commuting, and then we can take the diagonals if you plotted this out in a first quadrant array, which I'll maybe I'll do that in a second. Then if you just take the diagonals, you get this thing. This is called the total complex. Not to be confused with the tote that Mark is talking about, although it's actually related, but that's another thing. Okay, so now here's what we can do with this. Given a double complex, we can define a filtered chain complex as follows. We just take everything whose horizontal coordinate is greater than or equal to P. So let's see. So I will draw some sort of picture here. All right, so here's our double complex, and here's K00, K01, K02, K10, K11, K12, etc. And then the total complex is given by these diagonals. So there's C0, there's C1, there's C2, etc. So now, if I just pick a P there and look at everything to the right, or let's say P is here, and then I look at everything to the right of that and call that KP. That's a subcomplex because the differential is going like that. There's a D term and a delta term, right? So KP is a subcomplex. So this gives me a filtered complex. So a double complex gives you a filtered complex, and then that's where we were before. A filtered complex gives us an exact couple gives us a spectral sequence. So a lot of spectral sequences arise from a double complex. So now, let's see, now I'm just kind of going a little bit fast because we're sort of out of time, but I'll just sort of jot down the upshot of this. So the E1 term is going to be, so we have to think about this just a little bit, but you don't have to think about it too hard. The E1 term, well, let's see. In this diagram, I have the filtration, the subchain complexes are everything to the right of a given P. So the E1 term is going to be the quotient, so that would be like FP mod FP plus 1. So that's would be like the Pth column. You could sort of think of the E1 term in dimension P as being represented by the Pth column, and then the differential is induced from the differential in the total complex, but I've filtered away the delta because I modded out by P plus 1. I took FP mod P plus 1. So the only thing that's left is the D. So the E1 term is essentially the following. It's the cohomology or homology with respect to the total, well, it's the cohomology with respect to the total differential. By definition, it's this, but we can think of this as this. It's essentially the complex K. It's essentially the complex K with the homology of that under the differential D, which is the vertical differential, because I filtered out the horizontal differential. So you can verify this.
Your filtration goes like that?
Yeah, the filtration FP is Ki for, let's see, it's Ki for I greater than or equal to P, so it's everything to the right. So if I take FP mod FP plus 1, then the delta is 0 on that. But the D is not. So the E1 term is basically this. Now, the E2 term, well, now you have to do, now here's where you have to do this rigorously, you have to sort of do a little diagram chased by elements. But the basic idea is you're going to take an element in the E1 term, which is a D cycle, and you're going to chase, well, let's see, what do I want? I want to compute D1. I want to compute D1, right? I have an element in E1 is a homology class under D. So now I want to compute D1. So you just use the definition of the boundary homomorphism that came from the Serpent lemma, and you compute D1, and you find out that D1 is essentially delta. So the E2 term basically ends up being the delta homology of the D homology of K. So intuitively, the way we sort of do this intuitively is we take our double complex and we take homology this way, or cohomology, whichever, you know how. Take cohomology this way, see what you get, that's the E1 term. Then you take cohomology that way, and that's the E2 term. I mean, you can justify that. And let's see, the spectral sequence that arises in this way, since I took two non-negatively graded degrees, then we get the hypotheses of our convergence theorem are satisfied. So we get let's see. So I have the E2 term, and let's see. So now let me do the following. I'm going to write down. Oh, now there's another thing. Now you have to actually check this, but it's again this is they do this rigorously in Bott and Tu. It takes half a page or whatever. But you want to verify that the bigrading that you have on K, the P and Q bigrading, that actually gives you a bigrading on all the terms of the spectral sequence. So that might seem completely obvious, but you have to sort of check it. But basically, the E1 term has the same PQ bigrading as does the E2 term and the E3 term, and so on and so forth. So you can check that, and then we get the ER term of the spectral sequence is a bigraded thing, and the differential on the ER term, if you chase through the diagram and the definitions, the way I've set this up and indexed everything, the differential on the rth page will raise the P degree by R, and it'll lower the Q degree by the quantity R minus 1. All right, so that's how the differential goes. And the E infinity term of a spectral sequence, the E infinity term ends up being the associated graded of under that total differential. So we have this total complex that we got by taking the diagonals, and that has a filtration on it because it's a filtered chain complex, and the associated graded is the E infinity term. So that's the convergence statement. And then the last thing I'll say is, instead of doing it that way, just do it that way. So you can do the same thing. You can do the same thing and just filter the other way, and then you'll get a spectral sequence also converging to the cohomology of the same total complex, because the total complex is the same no matter which way you do it. But the other spectral sequence if you do it the other way, that'll have as an E2 term the D cohomology of the delta cohomology of K. In other words, you take cohomology this way, and then you take cohomology that way. So you have two different spectral sequences converging to the same thing, and that turns out to be whenever you, so here's a general principle. Whenever you have two, in any context, whenever you have two different spectral sequences converging to the same thing, then there's potentially a lot of information there, right? Because the two spectral sequences are different, but they're going to the same thing. So that forces all kinds of things to happen. That means that you can infer differentials in one from differentials in the other, and so on and so forth. And if they're graded differently, then that's even better, because something might be hard to prove in one, but then when you look at the same thing over in the other one, it's obvious because of the grading or something. And so you can play the two off each other. So this is a really simple example of that principle of two different spectral sequences converging to the same thing, giving you a lot of information. So in the double complex, in the typical applications of this, a lot of the time you'll have, so a typical thing that might happen is you'll look at one of the spectral sequences, and the E2 term will be something that's familiar, but you don't know what it's converging to. But then if you look at the other spectral sequence, that collapses at E2, and that tells you that the cohomology of the total complex is this other thing which you recognize, and that's going to be the target of the first spectral sequence, and now you have a spectral sequence whose E2 term you recognize and whose target you recognize. That's just a typical common scenario for how this kind of thing gets used, and then there's other examples too. So if we pursue this, if we talk about this some more at a later date, then for the follow-up talk, I guess the thing would be to just launch into some applications. Yeah, we look at there's a wonderful double complex called the Czech-Durand complex, and the result will be the relationship between Durand cohomology and Czech cohomology. There's the Serre spectral sequence, which can be done in singular cohomology or Durand cohomology, and it arises from a fibration or a fiber bundle of manifolds, and on and on. So for part 2, we'll just do applications and examples, I guess.
Who wants to hear about the
All right.
example?
Okay.
Yes.